Jnanam Paramam Dheyam. Knowledge is supreme.
So, let us try to do one example of this again to see what is happening, right, to understand. So, we will do this example, okay, so that you feel comfortable in computing things. So, T is from R2 to R2, T of xy is x plus 3y, 4x plus 7y. Okay. So, if I want to compute the matrix, what do I have to know? We have to have a basis on the domain and basis on the codomain. So, let us, for the simplicity, let us take the standard basis on both. Okay. On B on the domain, the basis is 1 0 0 1, and the same basis on the codomain. So, 1 0. I am just taking this because computation becomes slightly simpler, otherwise you have to solve equations and so on. Okay. So, what is T of 1 0 and what is T of 0 1? I have to find the matrix of T, right. So, what is T of 1 0? So, 1 and 0. So, first element is 1 and second element is 4. Is that okay? What is T of 0 1? X is 0, y is 1, so this is 3 and 7. So, what is that? I should write this as a linear combination of the basis elements there. So, that is simply 1 times 1 0 plus 4 times 0 1. This has become simpler because I have taken standard basis. Otherwise, I had to write alpha times this plus beta times that and solve those two equations, find values of alpha and beta, right. That will involve solving a system of equations. Here it is easy because it is just 0 1 1 0. Similarly, this is equal to 3 times 1 0 plus 7 times 0 1, right. So, what is the matrix of T? Matrix of T is 1 4 and 3 7, right. So, now I want to check whether T is invertible or not. So, question is T invertible? How do I check? Either I can check kernel of T is just 0, right, or the range nullity range of columns, that is range is a column space that has dimension 2, or here is determinant which is going to be very useful. This is a 2 by 2 calculation of determinant is very easy here. So, what is the determinant of this? 7 minus, right. So, that is equal to, that is not equal to 0. So, hence T is invertible. So, that is because our matrix is quite 2 by 2. So, computation is simple, even 3 by 3 it will be 3 by 3 also it will be okay, or you can just directly try to compute what you have T of 0 0. T of xy equal to 0 should imply x is equal to 0 and y equal to 0, that will mean T is 1 1, that is good enough. So, that will mean x plus 3y equal to 0, 4x plus 7y equal to 0, solve that equation and see that x comes out 0, y comes out as 0, that is proving T is 1 1, okay. That is also good enough. So, whichever you find easier in a particular example you can do that. So, T is invertible. So, what do we want to do now? So, what is the so if T is invertible, what is T inverse the matrix of this? I want to find the matrix of the inverse linear transformation, right. So, what will be that? By that theorem it says it is the inverse of this matrix. So, let us write that. So, by theorem T inverse the matrix of this is equal to, look at the matrix of T and find its inverse, right. So, given the matrix T, so this is the matrix T we had 1 3 4 7, I have to find what is T inverse of that, inverse T inverse. So, we will find T inverse of that, right, because it is nice and simple. You can do it by your adjoint method if you like, or you can do it by row operations, right, adjoin along with identity matrix. You remember that process, whichever is easier you can do that. It's clear. Okay. So, what you can do is to find this T inverse, you can start with the T. So, 1 4 3 7 and write 1 0 0 1 and transform it to using row echelon form. So, that the first part comes out as 1 0 and 0 and 1, and this will come out something, and that is precisely my inverse. That is another method of doing, or you can do it by, you have already found the determinant. So, if you use that method of adjoint, what was the determinant? Minus 5, right, minus 5. So, minus 1 over 5 adjoint method. So, what will be the first row, first column gone. So, what should I put here? 7, right. Then next one, this goes minus 4, and similarly this goes is minus 3, and that goes 1. So, that is the inverse, right. Now, not only I have found the inverse, I can now find what is my inverse linear transformation. So, let us compute T inverse of x y. What is that equal to? If I want to find out, I can even do that, because I have already gotten a matrix of it, right. So, what is T inverse of x y? So, let us write what is T inverse of. So, T inverse of x y is same as, look at the matrix of this of T inverse and multiply by that vector simply. So, it is minus 1 by 5, 7 minus 3, minus 4 1 multiplied by x y. That is, so what is it equal to? So, you can just multiply out and write down that vector. So, that is the expression for, okay, let us write minus 1 by 5. So, what will be 7x minus 4y. So, I am just writing it as a element in R2 instead of writing as a matrix. What is the second? Minus 3x plus y, right. So, that will be the formula for the T inverse, right. We started with T was, okay. So, I am just revising, T was x plus 3y, 4x plus 7y. With respect to that basis, we found out the matrix of this, because this is determinant not equal to 0 and actually equal to minus 5 determinant here. So, this is not this determinant is not 0. So, it is invertible, okay. Matrix of the inverse, what we do is we just look at, right, the formula from the theorem, that the inverse matrix of the inverse is inverse of the original matrix. So, given this we found out the inverse, and now using this I can find out what is my expression for the linear transformation T inverse, that also can be formed, okay. So, that we found out as. So, is it clear to everybody? Yes. So, basically what we are saying is, we are giving a association between a linear transformation and a matrices. If T is from V to W, V is dimension n and W is dimension m, then its matrix comes out to be order of m cross n, right, from the codomain to the domain, that is the order. For that you have to fix a basis on the domain and you have to fix a basis on the codomain. And how do you get the matrix? For the ith element of the basis element in the domain, compute the image, write it as a linear combination of elements in the codomain, using those bases in the codomain. The coefficients which come there, that give you the ith row of the matrix of that linear transformation. And this association is very nice. The matrix of the sum is equal to sum of the matrices, matrix of scalar multiple is scalar multiple of the matrix, and matrix of the composition is product of the original matrices, right. And as a consequence, this also tells you another way of finding what is the inverse linear transformation if you need be, right. Okay. So, that is about linear transformations and associate. The reason why we want to do convert linear transformations to matrices is because matrices are numbers, right, and all matrix operations can be put on a machine. Later on at the end of this course, I also tell you something called general vector spaces, which need not be subspaces of Rn. So, this concept of vector spaces is a more general concept. Okay. You can have objects, which objects can be added, which can be, for example, look at all 2 by 3 matrices, look at all matrices of order 2 cross 3, you can add them, you can scalar multiply them, and they behave as if they have all the properties that vectors have. Addition of 2 cross 3 is again a matrix 2 cross 3 closed under addition, closed under scalar multiplication. This matrix addition is commutative, it is associative, right, and scalar multiplication distributes. So, it has all the properties that we have for Rn, addition and scalar multiplication. So, matrices 2 cross 3 form a vector space, which is not of numbers, right. Its elements are matrices themselves. You can have many other. So, we will discuss it in the end of the course. There is the concept of general vector spaces, and whatever we have been doing, almost everything works for those vector spaces also, okay. And they are important for computation point of view. So, we will come to that a bit later. So, let us just come back to our thing that. So, idea is compute the matrix of T with respect to the given basis. Here it is B and B both, but you can have some different in the domain, different in the codomain. Check determinant is 0 or not equal to 0. If it is non-zero, it is invertible. If it is 0, it is not invertible, problem is over. And if it is invertible, if this determinant is not 0, you can find the inverse of that matrix by using our techniques, either by looking at reduced row echelon form or by adjoint method, whichever is, and then using that matrix you can write down the formula for T inverse of a vector, right, by matrix multiplication as we did last. So, this is matrices and linear transformations. Okay. Now, what we want to do next is, see, we have been trying to sort of do things which in R2, R3 and Rn, right, in a setting whatever is true for R2, R3 we try to extend it to Rn general settings. R2 there is a basis, so every vector subspace should have a basis, how to get a basis and so on, and maps on them. But on R2 and R3 there is another important thing, there is a notion of not only notion of distance, not only this notion of linearity, there is a notion of angle in R2 and R3. Given two vectors, you can find out what is the angle between those two vectors. Given two vectors in R3, you can find out what is the angle between them, right. And because of that, you can do lot of geometry, lot of more geometry can be done in R2 and R3. So, let us just revise that and see what we want to do. So, let us just revise R2 and R3, given two vectors A and B, A is A1, A2, A3, B is B1, B2. I am just looking at R3, R2 you can remove one component, same will work. So, this is what is called the dot product. We define in vector algebra, vector calculus, whatever it is, the dot product. A dot B is A1 B1 plus A2 B2 plus A3 B3. Advantage or in this notation, it also gives you what is called the magnitude of that vector. If you treat A as a vector, it has a length. Its length is nothing but A dot A So, that is a1 square plus a2 square plus a3 square square root, that is the usual Euclidean distance, Pythagorean distance between 2 points in R3, right. So, that is expressed in algebra now. See, now you see slowly geometry is being converted into algebra. Okay. That notion of distance, we define a dot b, that is a function R2 to R2, a comma b goes to a dot b, right, from R2 to scalars, and the magnitude is defined in that way, and this also gives the notion of angle. So, what is the notion of angle? A dot b is magnitude of a, magnitude of b into cos of the angle between them theta. So, here his definition of angle comes. What is the angle between them? I can define cos of that angle, right, by this expression. If they are non-zero vectors, I can divide by that. So, cos theta is equal to a dot b divided by norm of a into norm of b, right. So, the geometric notion of angle, right, measurement comes out in the form of algebra now, this equation. So, once that is there, you can say when is two vectors perpendicular and the angle between them is 90, that means a dot b is equal to 0. So, that gives you a notion, algebraic notion of perpendicularity of two vectors, that a dot product is equal to 0. So, that geometry being converted into algebra, basically keep that in mind, because the reason is you can do geometry in R2, you can do geometry in R3, you cannot do geometry in R4, you can't visualize that. So, but you want to do the same things. So, all these concepts carry over to R2, R3, R4, Rn, any, right. So, we can do everything. So, this is a standard basis, right, in R3 1 0 0 0 1 0, and what is the property of that? Any two of them are perpendicular to each other and magnitude of each one of them is equal to 1, right. We have seen many other, we have seen that basis for R2 or R3 need not be unique, there are many other bases, infinite number of bases possible actually, but each will have 3 elements. What is the advantage of these 3 vectors? Why did I chose in my example also, let us take standard basis, because computations become simpler. For example, if x is any vector, then its coordinate x, y and z are simply obtained as what is x? X is the vector dot 1 0 0. What is the component y? X y z, the vector dot 0 1 0, and so the third one is x y z 0 0 1. So, if I take the dot product of each one of any vector with each one of them, I get the coordinates of that. That is the advantage. Otherwise, how will I get the coordinates if it is a general basis? If instead of 1 0 0 0 1 0, if I had some other basis, then I had to write x y z equal to alpha times b1 plus beta times b2 plus gamma times, and then solve those 3 equations in theory variables to get alpha, beta and gamma. Those will be the coordinates of that vector with respect to that basis, right. I have to do a lot of work, but here simply have to take a dot product and I get it very easily. So, these bases which are in which each element is perpendicular to other element have an advantage. So, that is what I am saying here. If you have got some p, q, r, some other basis, then writing v this, actually you have to calculate them by solving a system of equations. So, I am telling you what is the advantage of having 1 0 0 0 1 0 and 0 0 1 over other bases in R2 and R3, right. So, this is normally given a name, such a basis is normally called a orthonormal basis. Each vector is normal, that means standardized, length is equal to 1 and orthogonal to each other. So, the two are combined as orthonormal, right. So, the standard basis of R2 or R3 is an example of a orthonormal basis. We will define it formally also, right.